Okay, so in this part of the lecture, we are going to look at how to decode codes. We have defined block codes. Now in the next part, we're going to see how we can actually decode a block code. So we start with the transmission of a code word X. So what we do is we pick a code word X from our code and we transmit X over a memoryless channel. So this is important because we will make use of the memorylessness property a lot while deriving the decoder. Then at the output of the channel, we observe a noisy vector X. So we have the following situation. We transmit a vector X over the channel. And we receive Y. And we have the situation that P of Y given X is given. We know we can actually calculate it as the sum from I equals 1 to n of P of Yi given Xi. Okay, and now we would like to know in the decoder, like to estimate one X hat that is closest as possible to X. So the decoding problem is from the noisy observation Y, like to infer the originally transmitted X. And what we do for inference is we maximize the a posteriori, so-called a posteriori probability P of X given Y. So we select some X hat, which maximizes the probability P of X hat given Y. So what is the most probable code word X hat given that we have received Y? And this, by maximizing this probability, we minimize the error rate of the code. So the goal of the decoder is to maximize this a posteriori probability. Starting from this a posteriori probability, we are going to simplify the problem and see how we can actually do the decoding. And we will use our good old friend, Bayes' theorem, to carry out the observation. So this is something that we should know by heart. P of A given B is equal to P of A and B, the joint probability, divided by P of B, or it's equal to P of B given A times P of A divided by P of B. So we start our maximization problem. So we maximize the a posteriori probability P of X hat or P of X given Y, and we do this for every possible code word. So we maximize over all Xi from the code word. So we try every possible code word. We calculate the probability P of Xi given Y, and we select the Xi which maximizes this probability. This is given by the argument. The arg tells us which of those guys maximizes the expression, and it will return this argument. So we use Bayes' theorem because we don't know P of X given Y, so we transform it into something that we know. What do we know? We know P of Y given X. So we use Bayes' theorem to transform it into a form that contains P of Y given X. That's given by this expression. So we have P of Y given X times P of X divided by P of Y. So now we can further simplify. So one observation that we can make is that whenever we change X, so we want to compute this expression for every possible X. Whenever we change X, P of Y doesn't change. So P of Y is a constant during the optimization, and it can be anything. We know that it's a constant, so it's a probability, so it's between 0 and 1, but it stays the same. So regardless of what p of y is, if it is constant, changing x will not depend on the value of p of y. So we can take it out of the optimization and we don't need to take care of p of y. So this is important to see because that is a trick that we make many times doing such decoder derivations. So p of y does not change during the optimization, does not influence the maximization. So we have the maximization over p of y given x times p of xi. So what is p of xi? That's the probability that we transmit a certain code word. That one we can also simplify, and we can also simplify p of y given x. First, we're going to simplify p of y given x. I said already on the previous slide, we have memoryless channel. So we use the definition of the memorylessness and write p of y given x as the product of p of yt given xt. So we take the product over the individual components of our vector and we calculate p of yt given xt. So now we simplify p of x, and we do this by assuming that all code words x are transmitted equally likely. So we assume that our input bits are uniformly distributed, and then the probability of selecting a certain code word is just 1 over m. So every code word is selected with the same probability, 1 over m, or 2 power minus k. So we have 1 over m times the product of p of yt given xt. And again, 1 over m is a constant, which doesn't change the maximization. So we can take it out and we don't need to see it because the xi that maximizes this term is the same as the xi that maximizes the whole term. So 1 over m can go out. And we have left with the product, p of yt given xt. So this is also what we call the maximum likelihood decoding rule, because this term is what we frequently call a likelihood. And the maximum likelihood decoding rule is based on the assumption that all the code words are equally likely. So if all the code words are equally likely, then the maximum a posteriori decoding rule becomes the maximum likelihood decoding rule. They are equivalent. So this is the maximum likelihood decoding rule. And how can we further simplify it? So first we need to note that this maximum likelihood decoder has a rather unsatisfying complexity, because the complexity scales exponentially with the number of data bits, because we need to try all 2 power k probabilities. So already if k is 100, 2 to the power 100 is an enormous number, it's a gigantic number. And therefore this decoder is only valid either for Gedanken experiments or for very short codes. But it's the optimum decoder, and that's why we need to take a close look at it, because it will allow us to derive bounds later on. So now we want to simplify this term, and therefore we're looking at a few special channels. So we start to look at the binary input AWGN channel, and p of yt given xt is replaced by the conditional channel probability density function. So we have the product of f of yt given xt. So now this is a rather nasty function because it's a product. Very often we don't like products. In engineering, we never like products. Products are ugly and nasty. We like summations. How do we get a summation from a product? The logarithm is our good friend. So we apply the natural logarithm. And we can just write a logarithm in front of this expression. Why can we do this? Because the logarithm is a monotonically increasing function, and it will not change the maximizer. So if some xi will maximize this function, the same xi will also maximize the logarithm of this function. So applying the logarithm doesn't change, and now we can replace the log of the product by the summation of the logarithms. So we have the sum over log of f of y given x. Now we can insert f of y given x, and there is hope that we can further simplify because the logarithm and the exponential in the AWGN channel, they will cancel each other. So in order to continue with the decoder, we assume that the bits are mapped to bipolar values in the following way. This is the definition we already used. So 0 is mapped to a +1, and the logical 1 is mapped to a -1. So the channel input is given by -1 to the power xt. Okay. So with this definition, we can insert f of y given x. So f of y given x is the usual Gaussian distribution. We have noise of variance sigma n squared. So it's 1 over square root of 2 pi sigma n times e to the power minus. Now we have yt, and the transmit symbol, which is the mean of the Gaussian distribution, of the conditional one. The transmit symbol is -1 to the power xt because of this mapping. So it's yt minus -1 to the power xt squared divided by 2 sigma n. So we go ahead, we apply the logarithm. So this is ln over this prefactor and minus this guy. So the exponential function and the logarithm, they cancel each other. And then we are left with the argument of the exponential function. Again, this is a constant. This does not depend on x. So we can neglect this constant in the maximization because we are interested not in the maximum value of this expression, but in the x that achieves the maximum. And because this is a constant term, we can just remove it because it will be the same for every x, so it will not be depending on x. So we have the maximum over the argument. So again, we can simplify a little bit. We have a constant here, and we have a minus here. These we can get rid of. That's what we do in the following. So we further simplify the parentheses. So it's a quadratic term, so it's yt squared plus -1 to the power 2 times xt minus 2 times yt times -1 to the power xti. So -1 to the power 2 times xt is equal to +1. Okay. So we have -1 over 2 times sigma n squared of yt squared plus 1 minus 2 times yt times -1 to the power xt. Again, this guy is a constant. So it does not depend on x. It's a constant. It doesn't change the maximization. So what we can do is we can get rid of it. So for the maximization, we can get rid of that guy. And then we have -1 divided by 2 times sigma n squared times -2 times yt times -1 to the power xti. So -1 and -1, they cancel each other. And this is another constant. First, this guy cancels, and we have a sigma n squared, which is a constant, positive constant, so it will not change the maximization. So the final result is the following. We maximize for every code word the sum from 1 to n of yt times minus 1 to the power xti. So this is essentially the correlation between the received sequence and the transmit sequence, modulated to plus and minus 1. So what we do is we just take the correlation from the received sequence together between the received sequence and every transmitted code word mapped to plus and minus 1, and we choose the one that maximizes the correlation. That's our maximum likelihood decoder. It's also called a correlation decoder. So let's do a quick example. We're looking at our old friend, the repetition code. We have two code words. We have first code word 000, and I'm going to use two different colors to describe the two code words. So this is x1, and the second code word is 111. This is equal to x2. So assume we transmit code word x1. So transmit x1, this is 000, and this gets mapped to +1, +1, and +1, because minus 1 to the power 0 is equal to +1. So then we have the following situation in the channel. We transmit a +1, and we have Gaussian, additive white Gaussian noise. So this is P of y given x equals +1. Actually, we denote it by f of y given x. So now assume we receive vector y, which is 3 plus 3.0, minus 0.5, and minus 0.8. So recall that yi is equal to minus 1 to the power x I 1, because we transmit xi, we transmit x1, plus some noise ni. So now what we need to do in order to decode is we calculate the correlation between y and the two possible code words. So we do it first for code word x1. We calculated the sum from 1 to 3 over yi times minus 1 over xi. 1. So this is equal to plus 3.0 times plus 1 minus 0.5 times plus 1 minus 0.8 times plus 1, and this is equal to plus 1.7. So, and then we do the same for x2. So we calculate the sum from 1 to 3 over yi times minus 1 power xi2. This is equal to plus 3.0 times minus 1 minus 0.5 times minus 1 minus 0.8 times minus 1, and this is equal to minus 1.7. And we see that clearly this one is larger or equal than the second one. So our decoder yields, calculate the arc of the maximum over all xi, and we maximize over the correlation yi times minus 1 to the power x, call this j, xj I, and this is equal to 0, 0, 0. So a transmit symbol was equal to 0. So despite the fact that we receive two negative symbols, we still decode for a +1. So we still assume that +1 is the more likely transmitted sequence. This is astonishing because if we had done a decision before, then we would just see +1, -1, -1, and we would possibly infer that a -1 has been transmitted. So why is this the case? This is the case because we have two types of noise. I call them good noise and bad noise. So what is good noise? So we transmit a +1. So the bad noise moves our received symbol closer to the decision region. So it gets closer to this region where it gets ambiguous. We cannot decide anymore, was it a +1, was it a -1? So assume also we transmit the -1. We look at something like this. So we transmit +1 and transmit -1. So if we transmit a +1, the bad noise will move it closer to this decision region. The good noise, on the other hand, the good noise moves the received point further away from the decision region. And this is very helpful because this one will tell us that it is very likely to be equal to +1 that was transmitted. Much more likely than a -1 because the Gaussian distribution will have faded by the time it reached a high value. So this +3 gives us a lot of confidence that a +1 has been transmitted. And these two values, they are somewhere in this region here. They are very unreliable. They are very unconfident. So they cannot really help the decision. But this guy will help the decision. And this guy says, look, +1 has been transmitted. And mathematically, that's what we do. So this guy has a lot of opinion, a lot of voice in the decision. That's why we decode a +1. Okay, so then we'll go a little bit further and we're looking at the binary symmetric channel. So we have seen the binary input AWGN channel and we're looking at the binary symmetric channel. So we're looking at the case delta smaller than 1/2, because that's the usual case. We assume that the number of errors is relatively small. And we start at the same equation with the maximum likelihood decoder. So we maximize over all possible code words x. And we apply the logarithm to p of y given x, which is the product of p of yt given xt. Same trick. We change the log of the product into a sum of the logarithms. And this is the logarithm of p of yt given xt. And we sum up over the logarithm. So what is p of yt given xt in this case? Reminder, p of yt given xt is equal to delta if yt is different from xt, and it's 1 minus delta if yt is equal to xt. So now we do this for every bit in the code word. So how often is yt different from xt? That's expressed by the Hamming distance between x and y. So we look at the Hamming distance between x and y, and this is the number of times x and xt is different from yt. And in this case, p of yt given xt is equal to delta. We have log in front, so it's log of delta. Now this, on all the other positions, we have n minus the Hamming distance between x and y. Such positions, we have log of 1 minus delta. So now we group everything that has x, because we maximize over x. So this is the distance between x and y times the logarithm of delta divided by 1 minus delta, plus a constant, which is L times log of 1 minus delta. So this is a constant, so we can remove it from the maximization. Doesn't change. And now we look closer at this term. So if delta is smaller than 1/2, this guy, we have something that is smaller than 1/2, and this is smaller than 1. So something smaller than 1/2 and divided by 1 minus delta, which is between 1/2 and 1, will be between 0 and 1. If we apply the logarithm to something that is smaller than 1, we end up with something that is negative. So this is negative if delta is smaller than 1/2, which we have assumed in the initial statement. This is negative. So instead of maximizing something negative times the minimum distance, or the Hamming distance, we can also minimize the distance. So multiplying by a negative constant changes the maximization into a minimization, and we can remove the constant. So the maximum likelihood decoder for the binary symmetric channel is the code word that minimizes the Hamming distance to y. This is why the Hamming distance was such a crucial measure for classical codes, which were mostly designed for the binary symmetric channel. So very, very crucial measure. And we have this very nice decoder, very simple decoder. So we just look at the minimum distance of our received word to every code word, and we pick this one code word that minimizes this distance. And then we are done with decoding. That's the maximum likelihood decoder for the binary symmetric channel. So to summarize, the maximum likelihood decoder corresponds to selecting the code word with the smallest distance to the received word. Again, it is unfeasible because we need to do or carry out a brute force search over all possible codes. So it's only feasible for very simple codes. So this already summarizes the decoders. We will also encounter the maximum likelihood decoder for the binary erasure channel later when we look at LDPC codes or in the tutorial, which I believe. So now in the next part, we're looking at the maximum likelihood decoder to a very special class of codes and get some theoretical performance limits. So with this, we wrap up this video, and I'm looking forward to seeing you in the next one.